Hello and welcome back to Coder Key. In this video, we're going to discuss another problem, that is counting set bits. In previous video, we have seen what is bitwise operators, and we have also solved a problem called checking whether the keyed bit is set or not. So let's say we are given with a number n, which is 9. Okay, so the binary representation is 1001, right? So number of set bits are 2. Similarly, if we are given with a number 6, the representation is 110, and the number of set bits are 2. Similarly, if we are given the number is 13, the representation is 1101, right? And the number of set bits is 3. So now let us say we are given with the binary number this. Okay, so now, okay, let's say we have two more bits, two zeros bits, and this number is 36 now, right? Now what we're going to do is we are going to iterate over the bits, and we're going to see if the last bit is set, then we're going to increment the counter. Okay, then we're going to increment the counter, and after each iteration we are going to left shift our bytes. Okay, so if it is 0, then we're going to add 0. Okay, so and we're going to left shift. Okay, then again we're going to add 0. Okay, again we're going to add 0, and we're going to left shift. Now we encountered 1, so we're going to add 1 to it. So the counter has incremented to 1, and we're going to left shift. Similarly for these also, and this also. Again we encountered 1, again we increment the counter, and we left shift. At last we're going to get all the numbers as 0, and hence we get the counter. So let's write the code for it. So first of all, let's initialize our counter to 0. Okay, now what we're going to do is we're going to run a while loop for num, okay, until the num becomes 0. And how I'm going to achieve checking whether the last bit is set or not is using the AND operator. Okay, and I'm going to do this. I'm going to explain you what I did over here. Okay, it's num, not n, just a sec. Okay, and what we do, after each iteration we increment the counter, right? No, before that we don't increment the counter, but we left shift our number, right? And then we return the counter, right? So let's see first of all what this is doing. Okay, what we are doing over here is we are counting, we are doing something like count is equals to count plus number and 1. Okay, number and 1. So this AND operator can be used to check whether the last bit is set or not. So what we had the representation as 00100, right? So 100100. Now if we AND it with 1, what we're going to get is 0000000. That is, all this is 0, so this part is 0. Okay, what we did in the next step is we are like number is equals to number, left shifting it with 1. So now our number became 010010, right? Again we are doing an AND operator. Okay, and we got what? 0000000. Again we haven't got the last bit as 1. Again we we left shift our operator, right? We left shift our by bit, and we AND it with 1. Now we got 1, so 100000, and hence we increment the counter by 1. So counter was initially 0, now it became 1, so 0 plus 1 is 1, right? Now again what we do is we left shift, and this goes on. Okay, and at last when all this will be 0, okay, and when all this will be 0, then we will stop a loop. That is this, that is ensured by this, that is num. Okay, while num is true, that is it is not 0, until then we need to run the loop. Let us try running the program. No, yeah, so we are checking it for number 9. Okay, and that is 2. Similarly, we have checked for number 3, right? Sorry, 13, right? So let's see what we have. We have set as 3. Now let us check for 36, an example which we have taken. Sorry, right? So 2 is the thing. Now, one more very simple method that I would like to mention is language specific, but what you can do is you can just convert the number to binary. Okay, convert the number to binary and just count number of ones in it. This is very language specific code. In C++ also you might have a built-in method which can do this. Okay, so we're going to get 2. Okay, yeah, but it is language specific, but this is the logic. Okay, this is the logic. Yeah, the complexity of it is big O of log n. Big O of log n. Why log n? Because the number of bits of any number is log n. That is the length of bits. Okay, because we are iterating over the whole length of bits, so log n. Okay, so the time complexity is log n and the space complexity is big O of 1. We're not taking any space, so we'll write the time complexity and space complexity over here. Yeah. So another method, that is Kernighan's algorithm. The name of the scientist is Kernighan's. Okay. So what it said is it is based on very nice concept of ANDing the number and the number before it. Okay, let us understand this first. Okay, what we have the number, the same number that we had, that is 1 0 0 1 0 0, right? What we're going to do is we're going to subtract 1 from it. Okay, and the answer is going to get and with the number that we originally had. So the subtraction of this will be 2 1 0. It's going to get it's going to borrow the bits and no borrowing over here, and we're going to subtract it. That is 1 1 0 0 0 1. Now this number is going to get and with the original number that we had, that is 1 0 0 1 0 0, right? And now what we had is 0 0 0 and 0 0 1. This part is going to be same. This part is going to be same. The number before the first bit, the first set bit, and the rest all will be zeros. Okay, the first set bit and the number and the bits after it will be zeros. So this is it. Okay, so this is a new number now. Okay, and for every iteration we are going to increment the counter. Initially it was 0 and now we had our first iteration, so we're going to increment the counter. Now we had our new n as this. Again we're going to subtract 1 from it. Okay, again 2 1 borrow 1 borrow 1 borrow 1 borrow 1, and we're going to subtract it like 1 1 1 1 1 0, right? And now we're going to AND it with the original n that we had, that is the new n that we had, that is this. So 1 0 0 0 0 0. So we're going to get 0 0 0 0 0 0. Hence since we add one more iteration of it, so we're going to increment the counter to 1. Okay, and hence we got all zeros, and that is the time when we stop the loop. Okay, now let us code it. So first of all, we are going to have a counter initialized to 0. Now what we are doing over here is we are updating n by ANDing it with its predecessor. So n into n minus 1, so that is not n, it's num. Okay, n and n minus 1, right? And here we are incrementing the counter, but we are doing this until we have some value of n, so some value of number, right? And hence we are returning the count. Okay, again we're going to check for some numbers. Let's say we have 9 over here. Okay, just a sec. Okay, what happened? Okay, we need to print it. Just a sec. Yeah, so now we get 2 for 9. Let's check for 36. Yeah, so again the let's see if the time complexity will be bigger of log n. You know why? Because in worst case, let us consider that all the bits are 1, so it's going to get iterating. It's going to iterate over the length of bits that is present in this in the binary representation of that number, and that is log n. Okay, and similarly, the time complexity will be big O of 1. Okay, so yeah, these are the three methods that we have discussed. The first method is the simple method, iterating over the bits from last, and the second method was the binary, converting it to the binary representation and then counting ones in it. That is by using the library, the built-in function, and then using the Kernighan's algorithm. Okay, yeah. So this is it for this video. Make sure you subscribe, you send it to your friends. Okay, you press that bell icon and you like the video. One more thing I would like to mention is that there is a GitHub repository in the description, linked in the description, where you can check out all the codes of these particular of this particular playlist. Yeah, and yeah, so yeah, this is it. Thanks for watching.